here says that the limit of a constant is just equal to that constant. And so what that means is if you were to have a graph, that's not a very good graph, it's okay. But and I were to draw the graph of, for instance, this limit of 5 as x goes to 3, what's that going to be? You know what that means? No. Okay, so what it means, if this is like y equals 5. So say this is the line, it should have an arrow on both ends. But if this is the line y equals 5, right? And this is the y-axis and this is the x-axis over here. No matter what value I approach, no matter what x value I approach along this line, what is the y value always going to be? 5, right? So that's what this rule says. If your function is a constant function, then the limit, no matter what value you plug into that function, it's always just going to be equal to that constant. So this is equal to 5. What would this be? The limit as x goes to 0 of negative 8. Negative 8, okay? What this one says here is the limit of x as x approaches c is c. That's if your function is y equals x. Do you guys remember what y equals x looks like? Yes. It's we're going to put arrows on both ends. We're going to make it, we did that already. We're going to make it this dotted. Oh, I'm doing the wrong thing. I'm messing up. Let's make it purple. Let's have arrows on both ends. Arrows on both ends. Let's make it solid. Let's go like this. So if this is the graph, let's just say I'm going to have arrows on my letters. I knew that was going to happen. Sorry about the arrows. Yeah, you kids. So if this is the line y equals x, okay, then any value that I plug in here for x, what am I going to get out? I'm going to get out y. So if I were to plug in 5 into here, I would get out 5. If I were going to plug in 6 in here, what do I get out? 6, and so on. So that's what this rule says. So I can't really see this over here because it's too small, but let's make it bigger. Here we go. So I'm going to grab this, and I'm going to make it a little bit bigger so I can see what I'm writing. So I don't know why this green line is here. Do you? Limit of x, what's that say? Is that a 3?
That is a 3, yeah.
What's the limit of x as x goes to 3? 3. So that's just 3. What's the limit of x as x goes to negative 1/2? Negative 1/2. You say, this is stupid. Why do you have to know all these properties and stuff? It's just properties. And when you start doing more complicated limit problems and you're taking derivatives with limits and stuff like that, it's important to kind of manipulate these functions, okay? So all this says right here, this is another limit property that the limit of a sum is the sum of the limits, okay? So for instance, if I have this down here, the limit of x, and I'm just going to look at all 3 of these at once so I can look at these example problems. The limit of a difference is equal to the difference of the limit, and the limit of the product is equal to the product of a limit. So what that means is if I were doing some of these problems down here, which I'm going to do right now, is I can break these apart into various things. So that's is that a 3 or a negative 3? That's a negative 3. So I could break, this limit is equal to the limit as x goes to negative 3 of x plus the limit as x goes to negative 3 of 4. That's what that first property says, is I could break this into 2 separate limits, and then I can plug in negative 3 in there, and I get out what? Negative 3. And if what's the limit of 4 as x goes to negative 3? 4, and I add those together, and I get 1. And that's how you could do that if you wanted to. Now Now you say, why do I have to do that? I could have just plugged -3 in there and got the same answer. And the reason for that is when you get in, again, when you get into more complicated limits and you need to break it apart, you're allowed to do that. Same thing which go for this. I'm not going to do this one. It's kind of exactly the same thing. This one says I could break this into the limit as x goes to -5 of -4 times, I could break it into these two limits, times the limit as x goes to -5 of x. And what's this equal to? That's equal to -4, and this is equal to -5, and -4 times -5 is positive 20, okay? And you could do a similar thing for this. I don't think we need to do that one. This one you break into 3 parts. If you did want to do this one, you could just break it into the limit as x goes to 2 of 5 times the limit of x goes to 2 of x, because this is x times x, right? Times the limit again, limit as x goes to 2 of x, and then I could plug in all those values and get out the answer. Or I could just take 2 and plug it in there and get the answer, which is the easy way to do it. Okay? Questions yet? Good. We're moving on. Okay. So the next thing says, if I have a monomial function or a polynomial function, like this or like this, all I really have to do is plug in that number into the function and I'll get the limit, okay? And you say, well, what's the difference between, you might say, what's the difference between taking the limit of something and just plugging it in? Well, if it's a polynomial functions are smooth functions, okay? So, right, Austin?
Mm-hmm. Yeah.
Right? So if you remember from first semester, okay, like looking at this function right here, what does this function look like? Anyone remember? How many roots can it have?
I can't see it.
It's got at most 4 roots, and it's got to start from up. Remember this? It's got to start from up and end up, like that. And so that function might look something like that. And polynomial functions, they kind of go on forever and ever, but they don't have any holes in the graph or any asymptotes or anything like that, or any cusps. Cusps are things that look like that. And you get those, for instance, if you were to graph like x to the 3/2 or something, you'll get a cusp in your graph, a sharp point. And but polynomial functions are nice, smooth functions. And so for any x value that I approach on that polynomial function, the limit is going to be the same as the value that I would get out when I plug in the x value. Now that's not necessarily true with a function like this, because the limit and the value of the function are not necessarily the same thing. So for this case, for instance, I would just plug in 2 in here, and I would get out 5 times 2 to the 4th minus 6 times 2 to the 3rd plus 3 times 2 to the 2 plus 4 times 2 minus 2. And in that case, I get, I think that's 80. I think that's 48. No, is that 48? Yeah, 48. I think that's 12. I think that's 8. And I think that's minus 2. And I think if you add all that up, you get 50. Okay? So that would be the limit of this one. All right? Questions? You could do this the same way, but I'm not going to do that because that would be more than you need to know, more than we need to do. All right. So this one says that the limit of power is equal to the power of limits. So you can either take the limit of the inside function and then raise it to a power, or you could take the thing and plug it in, take the whole limit at once, okay? So for instance, like this one, I could have broken this into, I think we're going, no yawning. I'm going to say your name on the video, young man, in the front. And I'm going to send it to your parents. All right. So anyway, this one, you can write to limit as x goes to 1 of 3x minus 5, the whole thing raised to the 4th power. That's what that property says. So I can take the limit of this and then raise it to the 4th power, which would be the limit. All I have to do is plug this in, because this is really a polynomial function. It's 3 minus 5, which is negative 2. Is that negative 2? Yeah. Raised to the 4th power, which is 16. So that would be that limit. And you might say, why can't I just plug it in? You can. Okay? But again, when you're taking more complicated limits, then this property becomes useful. Just believe me. All right. And you can do the same thing with square roots. I like this one because a lot of you guys don't know how to deal with this one. You can do this. And we could just plug in and raise it to the 4/3 power, or you can take the limit of the inside function and then raise that to the 4/3 power. Well, if I plug in negative 1 in here, what do I get out? Let's see. Negative 1 cubed is negative 1 times 5 is negative 5, right? Negative 1 times negative 1 is 1, and plus 3, which gives you negative 1. What's negative 1 raised to the 4/3 power? Right, so this is the same as the cube root of negative 1 raised to the 4th power. Can I take the cube root of a negative number? Yes. Yes. Yes, you can take the cube root of a negative, because a negative times a negative will give you a negative. So this is what's the cube root of negative 1? Negative 1 raised to the 4th power, which is 1. So here I took this inside limit first, and then I raised that limit to the 4/3 power. Okay? Can I move on? Move in. Let's move. Let's move on. Okay. So then, she's learning good sitting up there. Learning them good. All right. So what this one says, if you have a function that's something over something, you can take the limit of the top and the limit of the bottom, and you can evaluate the limit that way. However, sometimes that's not always such a great thing to do, because in this case I can do that. I have to make this part bigger. But if the bottom is equal to 0, that doesn't work. So like this one right here, if you plug in, is that a 1? That's a 1. If I plug a 1 in here, that's okay. I get 5 minus 1 plus 2 over 7, which is 6/7. So that works fine, okay? However, if I try to do this one and I plug in a 3 in there, right, I get a 9 minus 3 minus 6 over 9 minus 9, right, which is 0 over 0, which is undefined or indeterminate. You can't tell anything from that. So does anyone remember what to do if you see something like that?
DNA.
No, it's not DNA. There's a hole. There's a hole. There's a hole. There's a hole. There's a hole in the bottom of the graph. Okay, so what you do? X, you factor, okay? And then you factor the top. X, what is a top factor to? A minus 3x plus 2. And then you can cancel this out, okay? Like that. And then you can plug this in, okay? And you get 5 over 6. See? Because remember, a limit is, as long as I don't touch that 3, I can, so when I'm canceling this out, I'm saying x cannot be equal to 3, but it can be equal to anything else. So if I plug this into this reduced function, once I've taken the whole out of the way, then I get 5, 6. And so that is the limit. As I get very close to 3, like 2.9999, you'll be very close to 5 over 6. Okay? Yes? Okay. This one, I showed you how to do this. This is just like that one I did on the graphing calculator. Okay? And so if you plug this into your graphing calculator, I'm not sure what you get. Is this the same function we had? Well, you get some number. I think it's like 0.5 something. I don't know. You get, is it 0.666? I don't know. But I don't want to do that one because I want to talk about the next thing, okay? Which is the most interesting thing, which is the rate of change. So find the limit of the average rate of change as x approaches 2 of this function. So what the heck does that mean? Okay? Let me show you what that means. I'm going to make a graph here. Okay? Here's a graph. What shape does this make? This makes a parabola. So you should pay attention to this. So just to refresh your memory, to find out where that parabola crosses the x-axis, x squared plus 3x, I can set it equal to 0. I can factor out an x from both of these. X times x plus 3 equals 0. So either x equals 0 or x equals negative 3, right? And so I get two intercepts, one at 0 and one at negative 3. And then I get this parabola that is facing upwards because this is a positive one. I'm going to try to sketch a parabola to the best of my ability, and the vertex is in between those two somewhere. Oh, that's a really bad one. Anyway, what I'm let's fix this last part. What? Wait, Parker.
What?
Were you being inappropriate?
No, I asked you if you had a stroke in the middle of drawing.
Maybe. Okay. So, what you're trying to find as your graph approaches 2, okay? So, at 2, and we're going to approach 2, Austin, wake up. Hey. As this approaches 2, okay, I don't want to know what the value is that it approaches, but I want to know what the rate of change is, the average rate of change. So if I call this like x over here, okay, x, and I make a little, remember these little slope triangles, maybe? Okay, this value we'll call f of x, and this value we'll call f of something else, f of 2, okay? And this x value is just 2, and this x value is just x, okay? So what I want to find is basically the, I'm going to draw it yellow. I'm going to make it dotted even. What I want to find is the slope of this line, because that's what that rate of change is giving you, right? It's giving you the slope of that line at this particular point. Well, you're approximating the slope between these 2 points, but as I get close, as this x gets closer and closer and closer to this point, I'm getting closer and closer and closer to the exact rate of change at that point. You follow me? Okay? And the way you write that is you want the limit as x goes to 2 of f of x minus f of 2 over x minus 2. And you could do this algebraically, okay? It's the limit as x goes to 2. Well, I know what f of x is. F of x is this function right here, x squared plus 3x. What's f of 2? Plug it in. 2, what do I get out? Yes, I heard someone say it. 10, right? F of 2 is 10, right? If I take 2 and plug it in there, I get out 10 over x minus 2. Unfortunately, when I plug in 2 in here, I get something over 0, which is undefined. So what should I probably do? Factor, okay? And every single time you do this, the top, one of those factors will be what's on the bottom. So that kind of helps with your factor. What has to be the other factor at this point? X minus 2, and x plus 5. Very good, Derek. Okay. Now I can go ahead and I can cross this out like that. And I can plug in my 2. And what do I get out? 7. Okay? So what that tells you, what I just did is I took the limit as this distance from here to here gets smaller and smaller and smaller. And so what I'm finding is the exact slope of that line. Okay? And that has a bunch of different names. That is called the instantaneous rate of change. Instantaneous rate of change. Okay? It's also the limit of f of x as x goes to 2. It's also known as the, guess what? The derivative. Okay? And this line right here also has a name, and that's called the tangent line. Okay? Right? It exactly touches at one point. So you're kind of learning some calculus here. As I move along this curve to different points, is that rate of change always going to be the same? No, right? If I were right here, the slope would be less. If I were right here, what do you think the slope would be? What would be the slope this way? 0, right? If I'm going this way, what would the slope be? Negative, right? And so that's what the derivative is. It's the rate of change of a function, and you use limits to figure that out. And that's really important for, like, say this is distance. Say this is a rocket ship taking off, and this is distance, and this is time. What am I finding if I'm finding the rate of change of distance over time? The speed, right? So if you're in a rocket and you're graphing the distance versus time, and you find that change at any given, that rate of change is changing all the time. As the rocket gets out of the atmosphere, you're finding the velocity at different points. That's how they can calculate, like, how fast your rocket's going. What if this is velocity up here? Say, yes, if this is velocity and this is time, then you find the rate of change of velocity, which is what? Acceleration. Okay, so there's all kinds of applications, like in business. It might be the rate of change of your profits or something, or of your sales or something like that. And that has all kinds of applications. The end. Yay!